Today I'm going to talk about this paper from molecular SLAM to autonomous drone exploration. So this is the kind of like content that we are going to cover. So usually in robotic tasks related to navigation and exploration, they use laser scanners or RGBD stereo camera, which produce a like dense map. But in a case, they are usually like very power consuming, heavy and big. So either they cannot like really attach to a drone, or they need some kind of like special expensive drones. But in this research, they focus on using only a like very cheap camera on a commercial drone around like $300. So first of all, I'm going to talk about the related works. So camera and the drone. Yeah. It's like one of the cheapest commercial products in world. Yeah, and it has like SDK, everything, and everything about it is open source. Yeah. So speaking of autonomous exploration, this is actually the first paper that presented in this field. So in this paper, they talk about like he talked about how to explore the environment in such a like this kind of grid, which like this part are the unknown environment, this part are the free environment, and these one are the like obstacles, and they detect some kind of frontiers to detect more of the environment. Actually, this is the first paper that I read like 5 years ago and implement. So like after that, there were some kind of works that related to. They talk about optimizing a utility function that somehow is a trade-off between discovered area and the travel cost. So these are some of the like papers in like related to these kind of like methods. So these pictures related to this one, which they use a laser scan, a 2D laser scanner, and this is the input that they have. And also there are like the other branch that they talk about like measuring information gain instead of like discovered area. So these are some of the works. So if you like see, there's one name that is like repeated in each of these works. So actually he's a like professor in University of Freiburg, and he's very famous in the field of robotics. And also he has a very like interesting book called Probabilistic Robotics, and it's very famous in that community. I think the last time that I checked, it was like around 8,000 citation, and it's him, and it's me. So, so in 2016, before the travel ban, he came to my country, and I have the chance to saw him. Yeah, it was very good. Also, there's like another type of exploration, which they care about like reducing the uncertainty of the map instead of like gaining information. Okay, so this is like the general kind of exploration that we have, and from now on, I'm going to talk about like the type of exploration specifically for drones. So this is one of the famous one. So they use a very expensive spinning 3D laser scanner and a stereo camera to detect and monitor like river paths. Also, so this is another like work that they like somehow pursue two objectives. One of them is that to maximize the information gain from 3D occupancy map, and the other one is like the high coverage of the surfaces that they travel, and they see actually in the like traveling. Also, this one uses a depth sensor. I think they use like Kinect, but I'm not sure. Uh, this is another work that it's done by University of Pennsylvania, and just very short thing that this guy is very famous in the field of drone. So he has like 2 or 3 maybe TED Talks. So it's very interesting and funny if you have any time. I recommend it. So actually, I'm not sure about this method because when I read their paper, I cannot understand like completely what's going on. But they don't like build a complete dense 3D map. Instead, they use some kind of like physical simulation to represent the like the environment to search for. And as you can see, they also have a laser scanner and a Kinect. This is another one. So in this case, which one is that? Oh, so for they don't use a frontier. They use next best view, which they like grow a tree, like a random tree, and then with this random tree, they choose the best branch. They choose the branch that probably has the best, like the most covered area after they going there. Okay. So now I'm going to talk about their method. So they use okay. So for their platform, they use an existing software package in robotic operating system for AR drone 2, which is this one, and then they change it for to be available for this one, which is Parrot BPOP. Okay, so I'm going to talk about like the specification of the BPOP, but before that, I think this video would be nice. So in this type of drones, they use a magnetometer, a gyroscope, and an accelerometer combined, and they combine together like initial measurement units. So they have like all the 6 degree, the 3 degree that the drone that can cover. So they can have like the idea about the degrees that the drone have in each kind of like axes, in each axis. They also combine ultrasonic air pressure and vertical camera for height. So this is actually in the drone that we have in the lab. It's also the same. They so this is usually like the down part. So they have camera and ultrasonics and then camera. So with with the height and also vertical movement. I think they use optical flow for vertical movement. They combine these together to get a like exact height information. And also this drone has a like fisheye camera. But if you see the output result, it's not fisheye. Actually, it's rectangular because they do some kind of like onboard stabilization. So even, I don't know if you realize that in the video, the drone was shaking like this, but the image does not have like, it does not have any effect from that. So they manually stabilize it on board. Actually, I just realized maybe some of you don't know that why we talk about like drones. Maybe I should talk about it at first. But anyway, so we are thinking about using a drone to for holding a pattern to calibrate a 360 camera. Actually, it's just an idea. So we are doing some kind of test. We are not sure if it's going to work or not. Okay. So at first, I'm going to talk about the navigation. So for navigation, they use one of the like previous work, which is called scalable navigation of a low-cost quadcopter with a monocular camera, which also they use a parrot to somehow have. So the thing that they do is that they have a like autonomous drone on some part of the like room, and when they do any kind of like forces to change the position of the drone, it's like automatically come back to the place that it was. So actually they use visual motion estimation plus attitude measurements, and because all of this data like transmitted through Wi-Fi, it has some kind of delay, so they use a extended Kalman filter to have the state of the system, and then they use PID controller based on that, like output of the extended Kalman filter state to control the waypoint of the drone. And also because like usually SLAM like okay, so for mapping we use a very like broad term. It's called SLAM, simultaneous localization and mapping. In these methods, usually they don't have any like metric measurement of the environment. So in this case, they use ultrasonic and air pressure to somehow get a like metric measurement of the SLAM. For their SLAM, they use LSD SLAM, which is also like introduced by them in like 2013, I guess. So SLAM is somehow a keyframe based SLAM. So they like consider only some reference frame, and then based on that reference frame, they track the motion of the camera. And then they somehow use graph optimization and mutual direct image alignment to globally to have a like globally consistent position for the like keyframes. And also one of the feature of LSD SLAM is like loop closure. So if they do some kind of like this movement and then they reach to this place, typically in like SLAMs, these 2 points don't match together. So they implement some methods to match these 2 points together, and they have like closed loop trajectory. What the problem is, because from this point to this point, when they reach to this point, and so they have position 2, and when they do the loop closure method, it becomes like 2 prime. So the position suddenly change a lot. So it can like somehow unstable the ECAF and the extended Kalman filter, and also the controller. So they said we use some kind of like offsets to solve this problem, but I don't understand what they mean by offset, because probably it doesn't work if they just like manually change the value. I don't know, but they only mentioned that we use an offset in the loop closure scenario to like stable the drone controller. Okay, and in the initial so for the exploration at the initialization step, the drone do some kind of like up and down hovering, and also in the same time it has a like 360 rotation. So they have like some kind of initial keyframes about the environment. Okay, so for the exploration, okay. Yeah, yeah. No, no, actually, so, okay. So, right, loop closure is actually a feature of LSTS-LAM rather than like the what we are going to talk about. So, in each part that they have some kind of like closed loop, LSTS-LAM do a loop, run the loop closure method. So for solving this problem, because it's actually I'm going to show you the videos. It happened a lot in their scenario because they developed something that is go and back and go. I will talk about it. So they have to address when the LSTS lamp reach to the loop closure part. What should they do to like reduce the unstability? Yeah, it's okay. Mm. Yeah, yeah. Okay. So for the exploration, actually, usually like for the drones that have dense map, they use a volumetric representation. But in LSTS LAM, it's not possible because we have a semi-dense representation of the environment. So and also we can have the depth information only for the part that have a very strong gradient in the image. Therefore, probably like most of the a large portion of the environment will be unknown in the initialization step. Okay, and also for exploration, it's very important because like to get somehow get a very like good depth from LSTS LAM, you should do some kind of like motion parallax movement to get the like depth precisely. So the exploration strategy should also consider these motion parallax. So before we go into the method that they use for exploration, this is the framework that they use for their occupancy map. So it's called like Octomap. An Octomap is an open source efficient implementation of occupancy mapping octrees. So speaking of octrees, the octrees is something like, if I can draw it, okay. So consider that we have a like 3 by 3 cube. So for the center, you put the center on a root of the tree, and each neighborhood become a branch of a tree. So this is called octree. Octrees that they use for the representation of the environment. So to implement this one, they use Octomap, which is like an open source efficient like implementation of these method. So let's consider that we have a like point cloud like this. The result in Octomap will become like this with like different resolution. Okay. So right now we are going to talk about like how they provide the motion parallax for the LSTS lamp. Okay, so to construct the like occupancy map from LSTS lamp, they traverse each keyframe with ray casting using the camera model. So they do something. So if this becomes, you want to see that? So if this with the camera, they do the ray casting, and they get the information for these parts of the occupancy map, like this. This one is one of the like example of how an environment will be look like after like calculating the occupancy map. So the blue voxels are like the occupied, and the green are like traversable. Okay. So to like calculate this motion parallax, at first they assume that we don't have any planarity for the textureless areas. So there is a problem actually. So if you can see, when they do the ray casting, they only have so if we consider these two are the gradient in the image, when they do the ray casting, they only have information about these two parts. Because we are not sure that if this part are a textureless area or it's like textureless area, or it's not like how can I say it? Or we don't have any information there. So they introduced something called lateral motion. So it's something like this. So they said if we want to like increase our information, we should do some like these sweeping the environment like this. So based on that, if we do this movement here, we will have the information from all of these voxels. Okay. So is it okay? Okay. So for like calculation of this direction, they model the problem like this. So these two are the features, and this is the motion. This is the motion of the camera. So to simplify it, at first they only consider about the motion, so they remove the magnitude, and then they calculate this area like this. So it's like a cross product of the vector to the feature and also the movement, and then they write this one as a skew symmetric matrix, and then they sum all of them together. So actually they sum twice of them together. I don't know why, but they just said we sum twice of them, probably because they want to like remove one of these coefficients. So this is the result, and then they replace this one into here, so it's become like this, subject to this one. So we have like a FAX and something that is equal to 0. So and with these two, they use Lagrange multipliers for the optimization. Okay, so this is the Lagrangian that they like and they calculate, and they get the like derivative of each one of them. So if you see this one, this is the definition of eigenvector. So the perfect motion, the direction of perfect motion should be in the direction of this matrix, which is like this big complicated matrix. It's so hot in here. Okay. So for like, so this actually for me, like eigenvector is always something very conceptual. So for understanding, like for having a physical like image of what will be the motion look like, they do a Monte Carlo simulation with 600 sample points, and they do the distribution. These three like normal distribution, which this one and this one is for the image size, and this one is the like their hypothesized depth. And they do like 100 round of simulation, and then they realize that the best direction for the optimal direction for increasing the free observing free space is the parallel motion to the image plane, either sidewards or like up and down motion. So based on that, they like introduce a strategy called star discovery. So in star discovery, so let's consider the drone. The center of the drone is here. So they calculate like these these four motions, and all of them are the degree are somehow predefined. I have to say, so when here they somehow like delay the loop, because so the drone, we are going to have like a movement like this and this, and so in each like part it has the loop will the loop is going to be closed, but because they said after like one part of the star discovery we don't have that much information about the environment, they postpone the loop closure until the end of a complete like a star discovery. So yeah. Also for global exploration, they define interesting voxel. So interesting voxel is a voxel that is known to be free, but is not in the line of sight of the previous origin of a star discovery. So for example, let's consider this example. So this is the first position of the drone, and it like this is the star discovery path. And when it come back, when it like do all of them and does all of them and come back to the origin, this part is become interesting because it's like it's supposed to be free, but it's not in the line of sight of the drone. So then it goes there, and again this part, like after star discovery, this part becomes so interesting, and then it goes there for further exploration. Okay, so this is the result of their work. So at first they do the initialization that just go up and down, and then they run the star discovery. If you see like the green or the star discovery path. And this is the occupancy map. Then they calculate. Actually, one of the things that I want to like mention right now is like consider that it's like 4 times faster. So the image looks like the normal movement, but it's like 4 times faster than what's happening in reality. So going to talk about, this is actually one of the limitations. This is actually one of the limitations of their work. And this is the second experiment. So this is like a much more bigger room than they do the experiment on it. So right now it performed the star discovery. Uh, yes. Yes, yes. I think right now, right now it's still in the star discovery part. So it's in the local exploration. Yeah, yeah. Actually, they show that. Yeah. So. Yeah. Ah, so they this is the in line of sight part, and then these parts are the parts that is like interesting for explorating more. So this is the path that it generates. Yeah. So and then yeah, because when it's like in a big room, there is no need for like a global exploration, because all of them is like somehow in a local neighborhood of the drone, I guess. So, in conclusion, so they provide a novel approach, completely only based on like vision based, only based on vision for navigation and exploration in micro area vehicles. So the strategy contains two part. The first one is like the local discovery, which is like they perform a star discovery, which so it's based on what they calculate in for the best motion direction, and they do the global exploration with like considering the interesting voxels. So there are two limitations in this work. One of them is that the quality of their exploration is like so tightly depend on the quality of tracking. So if they do like the fast movement, probably they're going to lose the track of the features. So they have to do very, very slow movement through the exploration. And also they do all of their computation on a computer like off board. So they transmit all of the information through Wi-Fi, and then the system do everything and send the data back to the drone. So this is one of the problems. They actually it's safe to say that in none of the time they have real time data from the environment. That's the reason they have to use like extended Kalman filter. Yeah, that was it. I think So probably I consider maybe I should explain more, I guess. I'm really sorry if it was not like obvious. Yeah. Thank you.